Empty space is not empty. This is not a philosophical observation or a poetic metaphor. It is a measurable, physical fact confirmed by decades of laboratory experiments. Right now, in any region of space you care to consider, including the space between the atoms in your own hand, quantum fields are fluctuating. Virtual particles are briefly materializing and vanishing, and a small but real pressure is being exerted on any surfaces placed close enough together to feel it. The vacuum of space has energy, it has structure, it has activity, and in the right conditions, that activity produces real, lasting, measurable particles from what appears to be absolutely nothing. In 1951, physicist Julian Schwinger calculated precisely how strong an electric field would need to be to pull real matter directly out of empty space. His predictions sat unverified for over 70 years. Then, using a material discovered in 2004 with properties unlike anything previously known, researchers created exactly that field in a laboratory. The Schwinger effect was confirmed. Matter emerged from the vacuum. To understand what that means, and why it required decades to verify, requires starting with what the vacuum actually is. Classical physics described a vacuum as the complete absence of everything. No particles, no fields, no forces, no energy. Remove all the matter, turn off all the fields, and what remains is pure geometric space with nothing in it. This picture is elegant, intuitive, and completely wrong. The problem became apparent as quantum mechanics developed in the early 20th century. Quantum field theory, the framework that unified quantum mechanics with special relativity and that underlies the standard model of particle physics, describes every particle not as a discrete object, but as an excitation of an underlying quantum field. The electron is not a small sphere with definite properties moving through space. It is a localized excitation of the electron field, which permeates all of space at all times. Similarly, the photon is an excitation of the electromagnetic field. The quark is an excitation of the quark field. And so on for every particle in the standard model. Each of these fields exists everywhere, always. You cannot remove them. The laws of physics are not separable from the fields they describe. Asking what space looks like with the quantum fields removed is like asking what water looks like with the wetness removed. The fields are not a property of space. They are, in a deep sense, what space is made of at the quantum level. This immediately creates a problem for the concept of a vacuum. If quantum fields are everywhere, what does it mean for a region of space to contain no particles? A vacuum, in the quantum mechanical sense, is defined as the state of lowest possible energy. It is the state in which no excitations of any quantum field are present. But the lowest possible energy is not zero energy. The Heisenberg uncertainty principle is responsible for this. The uncertainty principle is one of the foundational results of quantum mechanics. It states that certain pairs of physical quantities cannot both be precisely determined simultaneously. The more precisely you know the position of a particle, the less precisely you can know its momentum. The more precisely you know the energy of a system, the less precisely you can know the time at which it has that energy. This is not a limitation of measurement instruments. It is not that our tools are too crude to measure both quantities at once. It is a fundamental feature of how quantum systems work. The uncertainty is not in our knowledge of the system. It is in the system itself. At the quantum level, a particle does not have a precise position and a precise momentum at the same time. It genuinely lacks definite values for both simultaneously. For quantum fields in the vacuum, the uncertainty principle applies to the field values and their rates of change. A field cannot be both zero and changing at zero rate simultaneously with perfect precision. If the field is perfectly zero, its rate of change is completely undetermined, and vice versa. The result is that even in the vacuum state, quantum fields are constantly fluctuating. They jitter. They undergo random variations around zero that cannot be suppressed without violating the uncertainty principle. These fluctuations have energy. That energy is the vacuum energy, sometimes called zero-point energy. It is the irreducible minimum energy content of space itself, the energy that remains when everything removable has been removed. The vacuum fluctuations also create something else, virtual particles. In quantum field theory, a particle is a real excitation of a field that carries energy and momentum and can travel from one place to another and be detected. A virtual particle is something slightly different. Virtual particles are transient fluctuations of the quantum field that borrow energy from the uncertainty principle for a brief time and then return it. The uncertainty principle permits a region of space to temporarily contain more energy than the vacuum ground state, provided the energy loan is repaid quickly enough. The more energy is borrowed, the shorter the time before it must be returned. During that brief window, the energy can take the form of a particle-antiparticle pair materializing from the vacuum, existing for a moment, and then annihilating and returning their energy to the field. These are virtual particles. They cannot be directly detected while they exist, because any attempt to detect them would constitute the energy measurement that forces them to annihilate. But their effects on nearby real particles and on the properties of the vacuum are measurable. One of the most direct demonstrations of the reality of vacuum fluctuations and virtual particles is the Casimir effect. The effect was calculated by Dutch physicist Hendrik Casimir in 1948. He predicted the two uncharged, parallel metallic plates placed very close together in a perfect vacuum would experience an attractive force that could not be explained by gravity or electromagnetism. The explanation is based on the virtual particle structure of the vacuum. In the empty space outside the plates, virtual photons of all possible wavelengths materialize and vanish continuously. The wavelengths available are unrestricted. Between the plates, only virtual photons with wavelengths that fit the gap as a multiple of their half wavelength can exist. Long wavelength virtual photons that do not fit are excluded from the space between the plates but remain present in the space outside. This creates an asymmetry. The vacuum pressure from virtual photons is larger outside the plates than between them. The imbalance produces a net force pushing the plates together. The magnitude of this force depends on the plate separation, and it becomes significant at separations measured in nanometers. The Casimir effect was experimentally measured by Stephen Lamoureux in 1996, 48 years after Casimir's prediction, using careful experimental controls to eliminate electromagnetic effects and gravitational contributions. Lamoureux measured the attractive force between parallel plates in a vacuum and found it matched Casimir's quantum mechanical prediction to within 5%. Subsequent experiments have improved this precision considerably, and the Casimir effect has now been measured in numerous configurations using different geometries, different materials, and different separation distances. The agreement between theory and experiment is excellent. The Casimir force is real, and its reality implies that the vacuum is real, that virtual particles are real, and that the zero-point energy of quantum fields has measurable physical consequences. The Casimir effect has moved beyond physics laboratories into engineering. At the scale of microelectromechanic systems, devices with components measured in micrometers, and nanoelectromational systems, devices with components measured in nanometers, the Casimir force is large enough to affect device performance. Engineers designing microscale sensors actuators, and switches must account for the Casimir force in their calculations. Ignore it, and the device may behave unexpectedly, with surfaces sticking together or moving when they should not. Some researchers are exploring whether the geometry dependence of the Casimir force could be used constructively. Modifying the shape of surfaces can change the sign of the Casimir force, converting attraction to repulsion in some configurations. This repulsive Casimir force has been measured experimentally using specific material combinations. Levitation of microscale objects using Casimir repulsion, with no mechanical contact and no electromagnetic intervention, is a possibility being actively investigated for nanotechnology applications. The Casimir effect is one window into vacuum physics. The Schwinger effect is a deeper one, because while the Casimir effect demonstrates the energy content of the vacuum, the Schwinger effect demonstrates that the vacuum can produce lasting real matter under the right conditions. The theoretical groundwork for the Schwinger effect goes back to the 1930s. Walter Heisenberg, who formulated the uncertainty principle, and Hans Euler investigated the behavior of the quantum vacuum in strong electromagnetic fields. Their analysis, published in 1936, showed that in sufficiently strong electric fields, the vacuum would become unstable and begin producing electron-positron pairs. The electric field would effectively tilt the energy landscape of the vacuum, allowing the spontaneous appearance of an electron and a positron from the vacuum fluctuations, with the field providing the energy needed to make the pair real rather than virtual. Julian Schwinger formalized this prediction in 1951 with a precise mathematical derivation. His calculation showed exactly how the pair production rate depends on the field strength. The rate is exponentially suppressed for weak fields. For a constant electric field, the critical field strength required to produce pairs at a significant rate is approximately 1.3 times 10 to the 18th volts per meter. Written as words, that is 1.3 times 10 to the power of 18 volts per meter, or 1,300 quadrillion volts per meter. To put that number in physical context, a typical electric field inside a semiconductor device is on the order of millions of volts per meter. The electric field near an atomic nucleus is on the order of 10 to the 21st volts per meter, roughly 1,000 times stronger than the Schwinger critical field. So the Schwinger field is not beyond the scale of fields that exist in nature. It is achievable, in principle, near the surface of certain types of atoms. But in an extended laboratory setup, maintaining such a field over a macroscopic region requires an enormous concentration of electromagnetic energy. This is why the effect went unverified for so long. Building a laser powerful enough to create the Schwinger critical field in a useful volume of space is an engineering challenge beyond any facility that existed until very recently. The world's most powerful laser facilities, including the extreme light infrastructure in Europe and the National Ignition Facility in the United States, are approaching but have not yet fully reached the peak intensities required. However, a different path to verification became available through the discovery of graphene and the recognition of its unique electronic properties. Graphene is a single layer of carbon atoms arranged in a hexagonal lattice, 1 atom thick. It was isolated and characterized in 2004 by Andrei Geim and Konstantin Novoselov at the University of Manchester, work for which they received the Nobel Prize in Physics in 2010. Graphene's electronic properties are extraordinary. Electrons in graphene do not behave like ordinary electrons in a metal or semiconductor. They behave as if they have no rest mass, propagating through the graphene sheet at a speed equal to 1/300th of the speed of light, following the same equations that govern massless particles like photons. This behavior arises from the band structure of graphene. In most materials, The energy states available to electrons form two bands separated by a gap. Electrons in the valence band cannot move freely. Those promoted to the conduction band can carry current. In graphene, the valence band and conduction band meet at specific points in momentum space, called Dirac points, and in the vicinity of those points, the energy-momentum relationship is linear rather than the quadratic relationship seen in ordinary materials. This linear dispersion relation is exactly the relationship satisfied by massless relativistic particles described by the Dirac equation. The Dirac equation was formulated by Paul Dirac in 1928 to describe electrons in a way consistent with special relativity. One of its most significant predictions was the existence of antimatter. The equation has solutions corresponding to both electrons and their antiparticles. In ordinary materials, electrons follow the Schrödinger equation, not the Dirac equation. In graphene, electrons follow an effective Dirac equation, behaving as if they are massless Dirac fermions in two dimensions. This makes graphene a unique laboratory for quantum electrodynamics effects that would otherwise require extreme conditions. Because the electrons in graphene are effectively massless, they require far less energy to separate from their antiparticle counterparts, the holes in the valence band that play the role of positrons in the graphene system. The effective Schwinger critical field in graphene is dramatically lower than in free space. Because the effective speed of light in graphene, the velocity at which the effective massless particles travel, is only 1/300th of the real speed of light. Since the Schwinger critical field scales with the square of the particle's effective velocity, the required field in graphene is about 90,000 times weaker than in free space. This brings the required field into a regime accessible to laboratory electrical setups. An electric field applied to a graphene device can reach the effective Schwinger critical field and trigger the spontaneous production of electron-hole pairs from the vacuum of the graphene system. Experiments confirmed this in recent years. By applying controlled electric fields to graphene samples and measuring the resulting current with precision, researchers observed nonlinear current voltage characteristics consistent with Schwinger pair production. The observed pair production rate as a function of field strength matched the Schwinger prediction, modified for the effective parameters of the graphene system. The data agreed with theory across multiple field strengths and temperatures. This was the first laboratory confirmation of the Schwinger mechanism. Matter, in the form of electron-hole pairs with real energy and the ability to carry real current, was being produced spontaneously from the vacuum of the graphene system by an electric field. The Schwinger effect, predicted in 1951, was confirmed. The significance extends well beyond the specific result. It demonstrates that the quantum vacuum is not a passive background. It is a dynamical system that responds to external fields. Push the field hard enough and the vacuum yields real particles. The vacuum is, in this sense, the deepest reservoir from which matter can emerge. This connects to one of the most fundamental questions in cosmology. Where did all the matter in the universe come from? The standard model of cosmology describes the universe beginning in an extremely hot, dense state approximately 13.8 billion years ago. In the very early universe, the temperature was high enough that matter and antimatter were constantly being created and annihilated in equilibrium with the thermal radiation. As the universe expanded and cooled, this equilibrium eventually ended. Matter and antimatter annihilated, leaving behind radiation, but a small asymmetry existed. For every billion antiparticles, there were 1,000,000,001 particles. After annihilation, 1 particle per billion survived. Everything in the observable universe Every atom in every star and planet and human being is that surviving 1 part in a billion. The origin of this asymmetry, called baryogenesis, is one of the major unsolved problems in physics. For the asymmetry to exist, certain conditions must have been met, identified by Andrei Sakharov in 19. One of these conditions is a departure from thermal equilibrium in the early universe. Strong field effects, including Schwinger-type pair production in the intense fields present shortly after the Big Bang, may have played a role in generating or amplifying the matter-antimatter asymmetry. Understanding the Schwinger effect in detail is therefore not just a laboratory curiosity. It is potentially relevant to explaining why the universe contains matter at all. The vacuum also plays a central role in the dynamics of the strong nuclear force, the force that holds atomic nuclei together and that binds quarks inside protons and neutrons. The strong force is described by quantum chromodynamics, which is to the strong force what quantum electrodynamics is to electromagnetism. In quantum chromodynamics, the mediating particles are which carry a property called color charge, analogous to the electric charge of electromagnetism. One of the most striking features of quantum chromodynamics is confinement. Quarks are never observed in isolation. They always come in combinations that are color neutral, such as the 3 quark combinations that form protons and neutrons, or the quark-counterquark combinations that form mesons. The reason is that the strong force does not weaken with distance the way electromagnetism does. Instead, as quarks are pulled apart, the field between them concentrates into a tube of color field called a flux tube, and the energy in the tube grows with distance. At some point, the energy in the flux tube is large enough to create a new quark-antiquark pair from the vacuum, breaking the flux tube and producing 2 new particles rather than separating the original quarks. This mechanism, called string breaking in the language of quantum chromodynamics, is a strong force version of the Schwinger effect. The intense color field in the flux tube plays the same role as the electric field in the electromagnetic Schwinger effect. The vacuum of the color field is unstable in the presence of sufficiently strong color fields, and it responds by producing new quark-antiquark pairs. String breaking explains why isolated quarks are never observed. Whenever enough energy is available to try to pull a quark out of a hadron, the energy goes instead into creating new quark-antiquark pairs, producing new hadrons rather than free quarks. The vacuum of quantum chromodynamics is not a passive medium. It actively participates in the dynamics of the strong force by creating matter whenever the field conditions demand it. This makes the vacuum of quantum chromodynamics particularly rich and complex. The QCD vacuum is filled not just with the zero-point fluctuations of free fields, but with a condensate of quark-antiquark pairs and gluon, configurations that give it a non-trivial structure. The quark condensate, in which quark-antiquark pairs spontaneously form throughout the vacuum, is responsible for most of the mass of protons and neutrons. The masses of the quarks themselves contribute only a small fraction of the proton mass. Most of it comes from the energy stored in the gluon fields and in the quark condensate of the QCD vacuum. This is a striking result. The mass of ordinary matter, the mass that makes you heavy, the mass of the atoms in every object you have ever touched, comes mostly not from the intrinsic properties of quarks, but from the vacuum energy of the strong force. Matter is, in a quantifiable sense, mostly empty space filled with vacuum energy. The electroweak vacuum is similarly the Higgs field, which gives elementary particles their mass through the mechanism of electroweak symmetry breaking, is a quantum field that permeates all of space. The Higgs field's vacuum state is not at zero. The Higgs field has what is called a non-zero vacuum expectation value, The field settles into a state in which its average value throughout all of space is a specific non-zero number, approximately 246 billion electron volts in the language of particle physics, or equivalently about 44 times 10 to the negative 27th kilograms times meters per second. The scale set by the masses of the W and Z bosons. This vacuum value of the Higgs field is what breaks the symmetry between the electromagnetic force and the weak nuclear force, and what gives the W and Z bosons their masses. It is also what gives all the quarks and leptons their masses through the Yukawa coupling of each particle to the Higgs field. The electron is heavy because it has a significant coupling to the Higgs vacuum. The neutrino is nearly massless because its coupling to the Higgs vacuum is negligibly small. The vacuum of the Higgs field is stable, but it may not be absolutely stable. Calculations based on the measured masses of the Higgs boson and the top quark suggest that the current vacuum state of the Higgs field may be meaning it is stable against small perturbations, but might tunnel to a lower energy state if given a sufficiently large kick. This potential lower energy state is called the true vacuum, and the process by which the Higgs field would transition to it is called vacuum decay. If vacuum decay occurred somewhere in space, a bubble of true vacuum would form and expand at the speed of light. Inside the bubble, the laws of physics would be different. The masses of all particles would change. The chemistry of atoms would be altered. No physical structure, no star, no planet, no atom, no nucleus could survive the passage of the bubble wall. The bubble would spread outward at the speed of light with no warning and no possibility of avoidance. The good news is that the probability of spontaneous vacuum decay in any given region of space over the current age of the universe is calculated to be extraordinarily small. The metastability of the electroweak vacuum, if it is indeed metastable, is a property of the very deep quantum vacuum, and transitions to the true vacuum require quantum tunneling through an enormous energy barrier. The calculated lifetime of the current vacuum state is many orders of magnitude longer than the current age of the universe, perhaps as long as 10 to the 500 years or more. The presence of high-energy cosmic rays, which have been bombarding the Earth and other matter in the universe for billions of years with energies far exceeding anything achievable in particle accelerators, and the continued existence of the universe, provide empirical evidence that the vacuum has not decayed in our observable past. This is consistent with the calculations suggesting extreme metastability, but it does not mean the vacuum is perfectly stable, and the question of its ultimate stability is one that cosmologists and particle physicists take seriously. The question of vacuum energy also creates one of the most notorious problems in all of theoretical physics, called the cosmological constant problem. When Einstein developed general relativity, he found that his equations permitted a term representing a constant energy density uniformly distributed throughout space, which he called the cosmological constant. He initially introduced it to allow for a static universe and later discarded it. But after the discovery in 1998 that the expansion of the universe is accelerating, the cosmological constant was reinstated as the most natural explanation for the acceleration. The energy responsible for accelerating the expansion is called dark energy, and its properties are consistent with a cosmological constant. The measured value of the cosmological constant, obtained from observations of the accelerating expansion, corresponds to an energy density of approximately 6.9 times 10 to the negative 30 joules per cubic meter. This is an almost incomprehensibly small energy density. It is equivalent to the energy of one hydrogen atom spread across the volume of roughly 1 cubic meter. The problem is that quantum field theory predicts a vacuum energy density from the 0-point fluctuations of all quantum fields, that is, larger than this observed value by an enormous factor, depending on what cutoff energy scale is used for the calculation. The theoretical vacuum energy density ranges from 60 to 120 orders of magnitude larger than the observed cosmological constant. 120 orders of magnitude is 10 followed by 119 zeros. Even the most conservative estimates of the discrepancy are gigantic. This is the cosmological constant problem, and it is one of the deepest unsolved problems in physics. Why is the vacuum energy so much smaller than quantum field theory predicts? What mechanism suppresses it to the observed tiny value? No satisfactory answer exists. Supersymmetry, a proposed extension of the standard model in which every particle has a supersymmetric partner, would cancel much of the vacuum energy, because the contributions of bosons and fermions have opposite signs and would partially cancel. But supersymmetry has not been observed at the Large Hadron Collider at the energy scales where it was expected to appear. And even perfect supersymmetry would only reduce the discrepancy from 120 orders of magnitude to perhaps 60 orders of magnitude, leaving the problem largely unsolved. The cosmological constant problem sits at the boundary of quantum mechanics, general relativity, and cosmology. Solving it will likely require the same unified theory of quantum gravity that is needed to resolve the black hole information paradox and to understand the physics of the early universe. It is a problem that makes clear that our understanding of the quantum vacuum, despite the impressive achievements of the Casimir effect measurement and the Schwinger effect confirmation, is still fundamentally incomplete. The vacuum is also central to the phenomenon of Hawking radiation, which connects quantum vacuum physics directly to the physics of black holes. A black hole is a region of space-time from which not even light can escape once it crosses the event horizon. General relativity predicts that the region inside the event horizon is completely cut off from the external universe. Nothing that falls inside can ever come out. Stephen Hawking showed in 1974 that quantum mechanics modifies this picture. The vacuum fluctuations that occur in the space near a black hole's event horizon are affected by the extreme curvature of spacetime. Virtual particle and particle pairs that form near the horizon can be split by it. One particle falls inside while the other escapes. The escaping particle carries energy away from the black hole, which means the black hole loses mass. This process is Hawking radiation. The energy of the escaping Hawking radiation comes ultimately from the gravitational energy of the black hole. The black hole slowly loses mass through Hawking radiation, shrinking over an astronomically long time scale until it completely evaporates. The temperature of Hawking radiation is inversely proportional to the black hole's mass. A stellar mass black hole, with a mass many times that of the Sun, has a Hawking temperature of billionths of a degree above absolute zero, far colder than the cosmic microwave background radiation, which means that such black holes are currently absorbing more radiation from the universe than they emit. But as the universe cools and expands, eventually the background temperature will drop below the Hawking temperature of these black holes, and they will begin to slowly evaporate. A black hole with the mass of a small mountain, about 10 to the 12th kilograms, would have a Hawking temperature comparable to the current temperature of the cosmic microwave background and would be close to thermal equilibrium with the universe today. No black holes of this mass are known to exist, but if they did, they would be detectable through the gamma rays produced in the final stages of their evaporation. Hawking radiation has not been directly observed for astrophysical black holes because the signal is too faint, but analog systems in the laboratory, in which the physics of an event horizon is mimicked using flowing fluids or Bose-Einstein condensation, have shown evidence of the analog Hawking radiation process. The first convincing laboratory demonstration was reported in 2019. Using a Bose-Einstein condensate of rubidium atoms. The phonons sound like quantum excitations of the condensate, showed a thermal spectrum at the analog Hawking temperature, consistent with the quantum vacuum mechanism predicted by Hawking. These laboratory analogs cannot test the gravitational aspects of Hawking radiation, but they can test the quantum vacuum mechanism that underlies it. The confirmation that the analog Hawking radiation process produces a thermal spectrum is significant evidence that the quantum vacuum physics Hawking identified is real. All of these effects, the Casimir force, the Schwinger pair production, the strong force string breaking, the Higgs vacuum, the cosmological constant, and Hawking radiation, are manifestations of a single underlying reality. The quantum vacuum is not nothing. It is not a passive backdrop. It is a dynamical, energetic entity with structure, with fluctuations, with fields that respond to energy and curvature and produce matter when the conditions demand it. The intuition that nothing contains nothing, that empty space is inert and inactive, is simply wrong. It is wrong in a way that has been confirmed experimentally, and that has profound consequences for everything from the mass of protons to the expansion of the universe to the fate of black holes. One of the more striking implications is what vacuum physics says about the concept of a particle itself. We tend to think of particles as fundamental, as the basic building blocks that fields are made of. But vacuum physics inverts this. Fields are the fundamental objects. Particles are excitations of fields. The vacuum is the lowest energy state of all the fields simultaneously. A particle is a temporary perturbation of that state, a ripple in the field rather than a substance in its own right. This picture, called the field-theoretic picture, is the correct description of the fundamental constituents of nature according to the Standard Model. There are no little balls bouncing around. There are fields everywhere, and what we call particles are the discrete, quantized packets of excitation that these fields can carry. When an electron is detected, what has happened is that the electron field has been excited at a specific location, and that excitation has interacted with the detector. Between detections, the electron is not a ball at some position. It is a dilocalized excitation of the electron field, described by a wave function that extends over space. The vacuum is the state in which all fields are in their lowest excitation state, the ground state, with no real particles present. But as we have seen, the ground state is not a quiet state. It fluctuates. Virtual particles constantly appear and vanish. These fluctuations give the vacuum its energy, produce the Casimir force, make the vacuum unstable in strong fields, and, through Hawking radiation, allow black holes to slowly return their mass to the universe. The question of what lies beneath the quantum fields, whether fields are themselves composed of something more fundamental, is open. String theory proposes that the fundamental objects are one-dimensional strings vibrating in higher dimensional space, with different vibration modes corresponding to different particles. The different quantum fields of the Standard Model would then emerge from the dynamics of the string vacuum, the lowest energy state of the string theory. The vacuum energy problem and the cosmological constant would, in a complete string theory, have an explanation in terms of the string vacuum structure. Loop quantum gravity offers a different approach, proposing that space-time itself is quantized at the Planck scale, the length scale of approximately 1.6 times 10 to the negative 35 meters, at which quantum gravitational effects become important. In loop quantum gravity, space is not a smooth continuous background, but a network of discrete loops with quantized areas and volumes. The vacuum state of this theory is a specific configuration of this spin network, and the dynamics of the vacuum are related to the topology and geometry of the network. Neither string theory nor loop quantum gravity has yet produced a complete experimentally verified theory. Both make predictions that are in principle testable, but that require experimental capabilities beyond what is currently available. The Planck energy scale, at which quantum gravity effects become dominant, is roughly 10 to the 19th billion electron volts, far beyond the reach of any existing or foreseeable particle accelerator. Testing quantum gravity experimentally requires either indirect probes through cosmological observations or extremely precise low-energy tests, sensitive to quantum gravitational corrections. One promising avenue is the measurement of the quantum vacuum energy through precision cosmology. The accelerating expansion of the universe is driven by whatever energy is stored in the vacuum. Future surveys of the large-scale structure of the universe, measurements of the cosmic microwave background with higher precision, and observations of large populations of supernova will constrain the properties of dark energy with increasing accuracy. If dark energy is not a perfectly constant cosmological constant, but varies with time or space, that would indicate that the vacuum energy is dynamic rather than fixed, which would provide important clues about the fundamental theory of the vacuum. Another avenue is precision atomic physics. The energy levels of atoms are sensitive to the quantum vacuum through the Lamb shift. A small energy difference between hydrogen, energy levels that would be identical in a theory with no vacuum fluctuations, but that is split by the quantum vacuum. The Lamb shift was first measured by Willis, Lamb, and Robert Rutherford in 1947 and played a key role in the development of quantum electrodynamics. It has since been measured to extraordinary precision in hydrogen and in heavier atoms. The agreement between theory and experiment for the Lamb shift is one of the most precise verifications of any physical theory, confirming quantum electrodynamics to better than 1 part in a billion. The precision measurements that continue to push the agreement between quantum and experiment are simultaneously the most stringent tests of the theory and the most precise probes of the vacuum. Any deviation from the predicted Lamb shift would indicate new physics in the vacuum, possibly the signature of particles or fields not yet included in the standard model. The search for such deviations is one of the motivations for precision spectroscopy of exotic atoms, systems in which the electron is replaced by a muon, a heavier cousin of the electron, or in which a proton is replaced by other subatomic particles. Muonic hydrogen, in which the single electron of hydrogen is replaced by a muon, has a much smaller orbit because the muon is 207 times heavier than the electron. This smaller orbit makes the muonic system more sensitive to the internal structure of the proton and to quantum vacuum effects near the nucleus. Measurements of the proton charge radius using muonic hydrogen produced a value that initially disagreed with measurements from ordinary hydrogen, creating a controversy called the proton radius puzzle that drove years of experimental refinement. The discrepancy has largely been resolved through improved measurements, but the episode illustrates how precision, vacuum, physics can reveal subtle effects that challenge existing theory. The vacuum is, in the end, the most fundamental arena in all of physics. It is the stage on which all other phenomena are played out. Its fluctuations are not background noise. They are the source of mass, the engine of matter creation in strong fields, the mechanism through which black holes slowly evaporate, and the energy driving the expansion of the universe. Understanding the vacuum completely means understanding why the universe exists, why it has the matter it does, and what its ultimate fate will be. We have made extraordinary progress. The Casimir effect confirmed that the vacuum has energy. The Schwinger effect confirmed that the vacuum produces matter. The Lamb shift confirmed that vacuum fluctuations shift atomic energy levels. The measurements of Higgs boson properties confirmed that the vacuum has a non-trivial field structure. The accelerating expansion of the universe confirmed that the vacuum energy drives cosmic evolution. What remains unknown is far larger than what is known. The cosmological constant problem, the ultimate nature of quantum fields, the role of the vacuum in the origin of matter in the early universe, and the connection between quantum vacuum physics and the theory of quantum gravity are all open questions. They are open not because we have not tried to answer them. They are open because they require a depth of understanding that current physics does not yet possess. The experiments and observations that will push this understanding forward are underway. The next generation of cosmological surveys will map the distribution of dark energy across cosmic time. Precision laser experiments will probe the boundary between quantum mechanics and gravity. Using the quantum vacuum as a sensitive detector, quantum materials like graphene and topological insulators will continue to provide low-energy analogues of high-energy quantum field effects, making phenomena like the Schwinger effect accessible in tabletop experiments, and the ongoing development of quantum computing and quantum sensing. Technologies will bring unprecedented control over quantum systems, opening new windows into the vacuum. Physics has learned repeatedly that the most profound discoveries come from taking the quantum vacuum seriously. Every time a vacuum effect was dismissed as a curiosity or a mathematical artifact, it later turned out to be a window into fundamental reality. The Casimir effect is now an engineering concern. The Schwinger effect explains string breaking in nuclear physics. Hawking radiation connects quantum mechanics and gravity. The Higgs vacuum explains the masses of all known particles. The next discovery may already be hiding in the vacuum, waiting for the right experiment to reveal it. The vacuum is not nothing. It never was. And the more carefully we look at it, the more we find that it contains everything. If this kind of foundational science interests you, following the developments as they happen is genuinely worthwhile. The results coming from precision atomic physics, quantum materials, and cosmological surveys in the next few years will likely reshape parts of this picture. Subscribing keeps that on your radar without any effort. The universe created something from nothing, and it is still doing it right now, everywhere, all the time. We just needed the right tools to see it, to fully appreciate why the Schwinger effect took over 70 years to confirm in a laboratory. It is worth tracing the intellectual path from theoretical prediction to experimental realization. Julian Schwinger was one of 3 physicists who shared the Nobel Prize in Physics in 1965 for developing quantum electrodynamics into a fully consistent, relativistic quantum field theory. The other 2 were Richard Feynman and Sinatiro. All 3 independently developed different mathematical formalisms for the same physical theory, and all 3 formalisms were shown to be equivalent. Schwinger's approach was based on operator methods and was mathematically rigorous and self-contained. Feynman's approach used the path integral and the now famous Feynman diagrams. The synthesis of these approaches produced the most precisely tested theory in the history of physics. Derivation of the pair production rate in a strong electric field was a demonstration of the power of quantum field theory applied to the vacuum. His calculation showed that the rate at which electron-positron pairs are produced per unit volume per unit time depends on the electric field strength in a specific way. The rate is proportional to the square of the electric field times an exponential factor involving the ratio of the critical Schwinger field to the actual field strength. The exponential suppression means that for any field weaker than the critical Schwinger field by even a moderate factor, the pair production rate is negligibly small. This is why the effect is so difficult to observe. The transition from undetectable to observable happens over a very narrow range of field strengths, and the required fields are extreme. The critical Schwinger field corresponds to an energy density sufficient to create an electron-positron pair. each with rest mass energy of approximately 511,000 electron volts, within the space of 1 electron Compton wavelength. The Compton wavelength of the electron is approximately 2.4 times 10 to the negative 12th meters. This is a length scale characteristic of quantum relativistic phenomena for the electron. Creating a pair of particles with this energy within this distance requires a field energy density comparable to the rest mass energy density of the electron, which corresponds to the enormous field strength that Schwinger calculated. The path toward laboratory verification using graphene exploited a profound analogy between the behavior of electrons in condensed matter systems and the behavior of elementary particles in quantum field theory. This analogy is deeper than a superficial mathematical similarity. The crystal lattice of carbon atoms creates a potential energy landscape for electrons that gives rise to effective quantum mechanical behavior identical to that of massless Dirac fermions in 2 dimensions. The electrons do not actually become massless. They continue to have their standard rest mass, but their effective dynamics near the deep points of graphene's band structure are governed by an equation identical in form to the Dirac equation. With 0 rest mass, this mapping between condensed matter systems and relativistic quantum field theory has been one of the most fruitful developments in modern physics. It means that phenomena predicted in high-energy physics can be experimentally tested using tabletop condensed matter systems. The Schwinger effect is one example. The quantum anomalous Hall effect, which is related to phenomena studied in quantum field theory, is another. Whale fermions, which are massless fermionic particles predicted in high-energy physics, but never observed as elementary particles, have been observed as collective excitations in certain crystalline materials called Whale semimatter. The laboratory became a quantum field theory simulator for the Schwinger effect specifically. The graphene implementation required several additional steps beyond simply applying an electric field. The measurement had to distinguish spontaneous pair production from other current-carrying processes. In graphene, at low fields, electrons can tunnel between states through ordinary quantum tunneling, producing a current even without pair production. The Schwinger pair production rate has a distinctive dependence on field strength that differs from ordinary tunneling. It rises much more steeply as the effective critical field is approached. Isolating this distinctive signature required careful experimental control and analysis. The experiments used epitaxial graphene grown on silicon carbide substrates, and high-quality exfoliated graphene on boron nitride substrates. The measurements were performed at low temperatures to reduce thermal noise. The field was applied through gate electrodes, and the current was measured with precision electrometers. The data showed a nonlinear relationship between field and current that matched the Schwinger formula for pair production in the graphene system, including the characteristic exponential dependence over several orders of magnitude in current, and across multiple samples. The confirmation of the Schwinger effect in graphene opened new questions about what other quantum vacuum effects can be accessed through analog systems. The Schwinger effect is relativistic in origin, requiring the framework of quantum field theory. Its observation in graphene demonstrates that the effective relativistic physics of the graphene Dirac fermions is accurate enough to produce a genuinely relativistic quantum vacuum effect. This gives confidence that graphene and related materials can be used to probe other effects at the interface of condensed matter and quantum field theory. There is also a deep connection between the Schwinger effect and the physics of intense laser fields. As laser technology advances toward ever higher intensities, the possibility of directly observing the Schwinger effect in free space using focused laser beams approaches. The current record laser intensities are on the order of 10 to the 23 watts per square centimeter, achieved by facilities using chirped pulse amplification, the technique for which Donna Strickland and Gerard Moreau received the Nobel Prize in Physics in 2018. The critical Schwinger intensity, the laser intensity needed to produce the Schwinger field, is approximately 4.3 times 10 to the 29 watts per square centimeter. This is roughly 6 orders of magnitude, or 1 million times, beyond the current record. This gap is enormous, but it is not necessarily permanent. Multi-petawatt laser facilities are under construction in several countries. The extreme light infrastructure in Europe includes a 10 petawatt laser system. Projects targeting 100 petawatts and beyond are being proposed. Each order of magnitude increase in laser intensity brings the Schwinger effect in free space closer. At the same time, techniques for using multiple laser beams colliding at a point, or for using the enhanced fields near intense electron beams combined with laser pulses, could potentially reach the Schwinger threshold with lower absolute laser power. In 2018, researchers at the Gemini Laser Facility in the United Kingdom observed a related phenomenon, the Britt-Wheeler process, the creation of an electron-positron pair from 2 photons colliding. This process, predicted in 1934 by Gregory Britt and John Wheeler, was the last of the basic quantum electrodynamic processes to be experimentally verified. The experiment used an intense laser beam colliding with a beam of high-energy gamma rays, produced by another part of the laser facility. The collision of photons produced real electron-positron pairs, confirming the theoretical prediction. The Britt-Wheeler process is related to the Schwinger effect because both involve creating matter from pure electromagnetic energy. The Britt-Wheeler process requires 2 photons colliding, while the Schwinger effect involves a single strong field. Both demonstrate the fundamental interconvertibility of energy and matter that Einstein's mass-energy relationship expresses, extended into the quantum field theory regime where pair production and annihilation are possible. The mass-energy equivalence, expressed by Einstein's relation, is so familiar that its radicalism is easily forgotten. It states that mass and energy are the same quantity expressed in different units, related by the square of the speed of light. The speed of light in meters per second is approximately 300 million. So the square of the speed of light in the relevant units is 9 times 10 to the 16th. This means that 1 kilogram of mass contains 90 quadrillion joules of energy, equivalent to roughly 21 megatons of TNT, or approximately the energy released by the largest Tusk nuclear weapon ever detonated. This equivalence is why pair production is possible. An electron and a positron together have a rest mass energy of approximately 1.0 to 2 million electron volts. If enough electromagnetic energy is concentrated, it can materialize as the rest mass of a pair of particles plus whatever kinetic energy remains. The Schwinger effect and the Britt-Wheeler process are different ways of supplying this energy from the electromagnetic field. The inverse process, pair annihilation, is equally fundamental. When an electron and a positron meet, they annihilate, converting their combined rest mass energy into 2 photons, each with energy of 511,000 electron volts. Flying apart in opposite directions, the 2 photons must fly in opposite directions to conserve momentum. This annihilation radiation is the basis for positron emission tomography, the medical imaging technique in which a patient is given a radioactive tracer that emits positrons. The positrons annihilate with electrons in the body, producing pairs of photons that are detected simultaneously by sensors arranged around the patient. The coincidence detection allows the location of the annihilation event to be reconstructed, mapping the distribution of the tracer in the body. Medical positron emission. Tomography is therefore a direct application of the pair annihilation process, the same quantum field theory physics that underlies the Schwinger effect operating in the human body. The technology depends on the fundamental interconvertibility of matter and energy. At the quantum field theory level, the relationship between virtual particles and real particles is one of the subtler aspects of quantum field theory, and it is worth clarifying because the concept of virtual particles is often misrepresented in popular science. Virtual particles are not real particles that briefly exist and disappear. They are a computational tool used in perturbation theory, the mathematical framework for calculating quantum field theory predictions order by order in the counteraction strength when a real particle scatters off another real particle. The process is calculated as a sum over all possible intermediate states, each represented by a Feynman diagram. The internal lines in a Feynman diagram, the lines connecting vertices but not ending on external real particles, are called virtual particles. These internal lines represent propagators, mathematical functions describing how the influence of an interaction propagates through space and time. Virtual particles represented by these propagators do not obey the energy-momentum relationship satisfied by real particles. They are off-shell, meaning their mass is not fixed at the physical particle mass. They can have any effective mass, including imaginary mass, because they are intermediate calculational steps, not real physical objects. Despite this, the effects attributed to virtual particles are entirely real. The Casimir force exists. The Lamb shift exists. These effects are correctly calculated by summing contributions from virtual particles in the quantum field theory, perturbation, expansion. The virtual particles are the mechanism by which the quantum vacuum mediates these effects in the perturbative calculation. But they are not tiny entities popping in and out of existence in physical space. They are components of a perturbative approximation to the exact quantum field theory calculation. The exact quantum field theory description of the vacuum does not use virtual particles at all. It uses the exact vacuum state, the lowest energy eigenstate of the full Hamiltonian, and computes expectation values of physical observables in this state. Virtual particles appear only when the exact calculation is approximated by a perturbative series. They are useful and accurate tools, but they should not be mistaken for the physical content of the theory. This distinction matters when thinking about questions like whether virtual particles carry information or whether they can be directly detected. They cannot. Direct detection would make them real particles. The virtual particle picture is a computational artifact of perturbation theory, not a description of the physical vacuum. The physical vacuum has real zero-point energy, real field fluctuations, and real measurable effects. But the entities responsible for these effects are field excitations described by quantum field theory, not little particles winking in and out of existence. Understanding this distinction also helps clarify the Schwinger effect more precisely. The Schwinger effect does not involve virtual particles becoming real. It involves the quantum vacuum in the presence of a sufficiently strong electric field, evolving into a state that contains real particles. The exact quantum field theory description is that the vacuum state in the presence of a constant strong electric field is not the same as the vacuum state in the absence of the field. The strong field changes the vacuum, and the new vacuum is one that contains real particle-to-particle pairs. This is analogous to how the vacuum of quantum chromodynamics contains a quark condensate. The QCD interactions change the vacuum from the simple, empty state of free field theory into a state with non-trivial structure, including the quark condensate that gives protons and neutrons most of their mass. The presence of interactions modifies the vacuum in the Schwinger effect. The electric field modifies the vacuum in a way that produces real particles. The production of real particles from the vacuum by strong fields is directly observable in heavy-ion collisions at particle accelerators. When two heavy atomic nuclei, such as gold or lead, are accelerated to nearly the speed of light and collide nearly head-on, the collision creates a quark-gluon plasma, a state of matter in which quarks and gluons are not confined inside individual hadrons, but move freely in a hot, dense fireball. The electromagnetic fields generated by the colliding nuclei, which are highly Lorentz contracted and therefore enormously strong in the lab frame, can reach field strengths approaching the Schwinger critical field. Electromagnetic particle production from these fields contributes to the total particle yield in heavy-ion collisions. The plasma itself is a state of matter that existed in the universe approximately 1 microsecond after the Big Bang, when the universe was hot enough that the QCD vacuum was in a different phase, with deconfined quarks rather than the confined hadrons of ordinary matter. Heavy-ion collision experiments at the relativistic Heavy Ion Collider at Brookhaven National Laboratory and at the Large Hadron Collider at CERN recreate this earlier universe state of matter in the laboratory, allowing its properties to be studied. The strong field vacuum physics of the Schwinger effect and the thermal vacuum physics of the quark-gluon plasma transition are both accessible through these experiments. The quark-gluon plasma turns out to have remarkable properties. It is the most perfect fluid ever measured, with a ratio of viscosity to entropy density closer to 0 than any other known substance. This near-perfect fluidity means that the quark-gluon plasma flows with almost no resistance. Unlike ordinary liquids, which experience significant viscous damping, the low viscosity of the quark-gluon plasma is a prediction of the holographic principle applied through the ADS-CFT correspondence. A strongly coupled quantum field theory in a certain spacetime is equivalent to a weakly coupled gravitational theory in a higher dimensional spacetime, and the gravitational calculation predicts a specific minimum viscosity to entropy ratio. The measurements at RHIC and LHC matched this theoretical prediction, providing unexpected experimental support for the holographic principle. The holographic principle connects back to the vacuum in a surprising way. If the holographic principle is correct, the maximum amount of information that can be stored in any region of space is proportional to the area of the boundary of that region, not to its volume. This area scaling of information is the defining characteristic of a holographic theory. It implies that the three-dimensional volume of space does not contain three-dimensional degrees of freedom at the fundamental level. The information content of the vacuum, including all its quantum field degrees of freedom, is somehow encoded on a two-dimensional surface. This is a radical claim. It means that our experience of living in three spatial dimensions might be an emergent feature of a fundamentally two-dimensional quantum theory, similar to how a three-dimensional holographic image emerges from a two-dimensional holographic plate. The three-dimensional appearance of the universe would be an effective description, valid at ordinary scales, of an underlying reality that is fundamentally lower dimensional. The implications for vacuum physics are profound. If the vacuum is fundamentally two-dimensional at the level of its information content, then the quantum field theory description of the vacuum with three-dimensional field degrees of freedom is an approximate effective description rather than a fundamental one. The degrees of freedom of the three-dimensional quantum field theory in the bulk are redundant encodings of the degrees of freedom of the boundary theory. The vacuum fluctuations of the bulk theory are not all independent. They are correlated in ways determined by the holographic structure. Whether the holographic principle is exactly correct, approximately correct, or a useful approximation remains an open question. It is supported by the ADSEFT correspondence, which is a mathematically proven equivalence between specific theories, and by the viscosity measurements in heavy-ion collisions. But it has not been directly tested as a fundamental principle of nature at the vacuum level. The quantum information revolution of the past 3 decades has provided new tools for thinking about these questions. Quantum entanglement, the correlation between quantum systems that cannot be explained by shared classical information, has been recognized as a resource with operational significance. The entanglement entropy of a quantum system, a measure of how much entanglement a subsystem shares with its environment, has been connected to the area of the boundary of the region occupied by the subsystem in precisely the way that holography would predict. In quantum field theory, the entanglement entropy of a spatial region is proportional to the area of its boundary, not to its volume. This is the same area scaling that characterizes holographic information. The connection between entanglement entropy and holography suggests that entanglement in the quantum vacuum is the physical origin of the holographic structure of spacetime. Spacetime geometry might emerge from the pattern of quantum entanglement in an underlying quantum system, with the geometry of space being determined by the entanglement structure of the vacuum. This idea, called entanglement entropy and emergent spacetime, is an active area of theoretical research. It connects quantum information theory, which began as a tool for understanding computation and communication, to fundamental questions about the nature of spacetime and the quantum vacuum. The insight that space might be built from entanglement is one of the most striking developments in theoretical physics of the past decade. The vacuum, then, is not just the lowest energy state of quantum fields. It might be the source of space itself. The entanglement of the vacuum state across different regions of space might be what creates the geometric relationships between those regions, producing distance and locality and the metric structure of spacetime from purely quantum mechanical correlations. Testing these ideas requires connecting them to measurable predictions. Some recent work has suggested that the entanglement structure of the vacuum near the horizon of a black hole's is directly related to the black hole's entropy, providing a more precise version of the Bekenstein-Hawking formula that relates black hole entropy to horizon area. If the entropy of a black hole is the entanglement entropy of the vacuum across the horizon, then information about what falls into the black hole is encoded in the entanglement structure of the vacuum outside, potentially resolving the information paradox. This resolution requires a precise accounting of how the entanglement of the vacuum evolves as the black hole evaporates. Recent developments in this area, using techniques from quantum error correction and holography, have produced what is called the Page curve calculation. The Page curve describes how the entropy of Hawking radiation should evolve over the lifetime of an evaporating black hole if information is conserved. In 2019 and 2020, theoretical calculations using the replica trick and the island formula in holographic quantum gravity produced results consistent with the Page curve, suggesting that information is preserved and escapes in the Hawking radiation through quantum gravitational effects not captured in the original Hawking calculation. The island formula involves a modification of the formula for entanglement entropy in the presence of gravity. In flat space quantum field theory, the entanglement entropy of a region is proportional to the area of its boundary. In the presence of gravity, quantum gravitational effects add contributions from regions called islands, which are regions of spacetime seemingly disconnected from the region whose entropy is being calculated, but that contribute because of quantum gravitational tunneling effects. Including the islands changes the entanglement entropy calculation in exactly the way needed to produce the Page curve. suggesting that black hole evaporation is unitary and information is preserved. This is not a complete solution to the information paradox. The calculation was performed in specific low-dimensional models of quantum gravity and may not directly extend to four-dimensional black holes. The physical mechanism by which information escapes in the Hawking radiation is not yet fully understood at the level of specific microscopic degrees of freedom, but the calculation represents significant progress in understanding how quantum mechanics and gravity can be reconciled in the context of black hole evaporation, with the quantum vacuum playing a central role throughout. The quantum vacuum thus sits at the intersection of the deepest problems in modern physics. It is where quantum mechanics and general relativity conflict most sharply. It is where the origin of mass is explained. It is where the matter content of the universe was generated. It is where the expansion of the universe is driven by dark energy. It is where the Schwinger effect converts electromagnetic energy into real matter. And it may be where space-time itself emerges from quantum entanglement. The experiments that will advance understanding in the coming years and decades span an enormous range of scales and techniques. At the smallest scales, precision atomic physics measurements using optical clocks and quantum sensors will test the quantum electrodynamic vacuum with ever higher precision, looking for deviations that would indicate new physics. The best optical atomic clocks now keep time with a fractional uncertainty of approximately 1 part in 10 to the 18th, meaning they would neither gain nor lose a second in longer than the current age of the universe. At this precision, they become sensitive to gravitational redshift from height differences of 1 centimeter, 2 variations in fundamental constants, and potentially to quantum vacuum effects beyond the standard model at slightly larger scales. Experiments with Bose-Einstein condensates, ultra-cold gases of atoms cooled to temperatures within billionths of a degree of absolute zero, provide clean quantum systems where vacuum effects can be studied in controlled conditions. Laboratory analogues of Hawking radiation, the Unruh effect, and cosmological particle production have all been demonstrated or proposed using Bose-Einstein condensates. These experiments cannot test gravity directly, but they probe the quantum field theory mechanisms that underlie gravitational quantum effects at the largest scales. Cosmological surveys mapping the distribution of galaxies across billions of light years will constrain the properties of dark energy with unprecedented precision. The Euclid Space Telescope, launched in 2023, will map the three-dimensional distribution of galaxies across 10 billion light-years of cosmic history. The Vera Rubin Observatory, currently beginning operations, will survey the southern sky in optical light with a depth and breadth never before achieved. The Nancy Grace Roman Space Telescope will provide complementary infrared observations. Together, these surveys will measure the equation of state of dark energy, the ratio of its pressure to its energy density, to within a few percent over a range of cosmic history. Any deviation from the constant value -1 predicted by a simple cosmological constant would indicate that the vacuum energy is dynamic, and at intermediate scales, quantum materials continue to provide new platforms for testing quantum field theory effects in the laboratory. Topological materials, graphene heterostructures, superconducting circuits, and photonic systems are all being used to realize effective quantum field theories with tunable parameters. The boundary between condensed matter physics and high-energy physics is becoming increasingly permeable, with insights flowing in both directions. The techniques developed for quantum computing and quantum error correction are being applied to quantum simulation of field theories that are computationally intractable by conventional means. The quantum vacuum is the central object in all of this. Understanding it completely is the unfinished project that connects the Casimir force measured in a precision laboratory to the expansion of the universe. The Schwinger effect confirmed in graphene to the origin of mass in the quark condensate, and Hawking radiation in analog systems to the ultimate fate of black holes. The vacuum is not nothing. It is everything that remains when you have taken away everything you can take away, and what remains is extraordinary. If you have stayed with this explanation through to the end, you already have more context for these questions than most people who discuss them. Following the developments as they come, whether from precision atomic measurements, quantum materials, experiments, or cosmological surveys, keeps that context current. Subscribing does that automatically, without any additional effort on your part. Space is full of something. We know what some of it is. We are finding out what the rest is. And the answer, when it is complete, will change how we understand the ground. Beneath all of physics, one of the most illuminating ways to appreciate how far the field has come is to trace the history of what physicists have called the vacuum at different stages of understanding. Before quantum mechanics, the vacuum was simply the absence of matter and radiation. It was the container in which physics took place, not a participant in physics itself. The ether, a hypothetical medium proposed to carry electromagnetic waves, was the closest thing to a physical vacuum in 19th century physics. When the Michelson-Morley experiment in 1887 found no evidence for the ether, the vacuum became even more purely nothing, a geometric stage for classical mechanics and classical electrodynamics. Quantum mechanics changed. This first with the uncertainty principle, and second with the development of quantum field theory. The uncertainty principle, as applied to the electromagnetic field, implies that the field cannot be exactly zero everywhere. Field fluctuations are unavoidable. Quantum field theory then provided the framework in which these fluctuations are described as virtual particles. The vacuum became a seething, fluctuating medium with measurable energy, content and measurable effects on real particles. Moving through it, the development of in the 1940s was essential to making quantum field theory workable. The zero-point energies of quantum fields, when summed up naively, produce infinite results. Every frequency mode of every quantum field contributes a half-gunnet of zero-point energy to the vacuum. And there are infinitely many frequency modes. The sum diverges. Renormalization is the procedure by which these divergences are systematically handled by absorbing them into the definitions of physical quantities, like particle masses and coupling constants. After renormalization, finite, calculable predictions emerge for physical observables. The Lamb shift was the first physical effect that required renormalization to calculate correctly. Willis Lamb measured the energy splitting between two states of hydrogen that the earlier Dirac theory predicted should be exactly degenerate in 19. The splitting was small, approximately 1060 MHz in frequency units, but it was precisely measurable by the microwave techniques developed during World War II. Hans Bethe performed the first successful theoretical calculation of the Lamb shift within a few months of Lamb's measurement, using a rough renormalization procedure. The agreement between theory and experiment launched the development of renormalized quantum electrodynamics. The Lamb shift arises because the electron in a hydrogen atom is not isolated. It continuously interacts with the virtual photons of the electromagnetic vacuum. These interactions cause the electron's effective mass to be slightly different from its bare mass, and cause the electron's energy levels to be shifted from the values predicted by the Dirac equation for a bare electron. The shifts are calculable and agree with measurement to better than 1 part in 10 million. One of the most precise agreements in all of science. The anomalous magnetic moment of the electron is an even more precise test. The Dirac equation predicts that that the electron's magnetic moment, the strength of its interaction with a magnetic field, is exactly twice the value expected from classical physics. Quantum electrodynamics predicts small corrections to this factor of 2, arising from the interaction of the electron with virtual photons. The corrections have been calculated to the 5th order in the coupling constant, involving Feynman diagrams with up to 5 internal loops, each requiring enormous computational effort. The theoretical prediction agrees with the experimentally measured value to 10 significant figures. This level of agreement is only possible because quantum electrodynamics correctly describes the quantum vacuum and its effects on the electron. The virtual photons that contribute to the Lamb shift and the anomalous magnetic moment are the same virtual photons that produce the Casimir force. The vacuum is a single physical entity, and different measurements probe different aspects of the same underlying physics. The renormalization group, developed by Kenneth Wilson in the 1970s, provided a deeper understanding of what renormalization means physically. Wilson's approach showed that quantum field theories should be understood as effective descriptions, valid at a particular energy scale, with different physics described at different scales. The quantum fields and coupling constants in the theory are not absolute. They depend on the energy scale at which they are probed. Vacuum fluctuations at different energy scales contribute differently to physical and the renormalization group tracks how the effective description changes as the energy scale changes. This picture implies that what we call the vacuum depends on the energy scale at which we observe it. At the energy scales accessible in ordinary atomic physics, the vacuum is well described by quantum electrodynamics with its electron and photon fields. At higher energies, the weak nuclear force and the Higgs field become relevant, and the vacuum must be described by the full electroweak theory. At still higher energies, the strong nuclear force and its quark and gluon fields must be included, and the vacuum of quantum chromodynamics with its quark condensate becomes the relevant description. At energies approaching the Planck scale, quantum gravitational effects modify the vacuum in ways not yet understood. This energy scale dependence of the vacuum is directly observable. The coupling constants of the fundamental forces change with energy scale. The electromagnetic coupling constant, which measures the strength of the electric force, is approximately 1 divided by 137 at low energies but approaches 1, divided by 128 at the energy scale of the Z boson mass. The strong coupling constant decreases at high energies, a phenomenon called asymptotic freedom discovered by David Gross, Frank Wilczek, and David Politzer, for which they received the Nobel Prize in Physics in 2004. These variations in coupling constants are predictions of the renormalization group applied to the quantum vacuum, and they have been precisely verified by accelerator experiments. The unification of the electromagnetic, weak, and strong forces at high energies is suggested by the convergence of their coupling constants. Calculations and supersymmetric extensions of the Standard Model show that the 3 coupling constants converge to a single value at an energy of approximately 10 to the 16 billion electron volts, roughly 10 million billion times the mass of the proton. At this grand unification energy, the vacuum may be described by a single unified theory in which the 3 forces are aspects of a single interaction, and the vacuum structure of this unified theory would determine the physical constants of the low-energy world. Grand unification has not been directly tested because the energy scale is far beyond any existing accelerator, but it has testable indirect consequences. The most important is proton decay. In grand unified theories, protons are not absolutely stable. They can decay into other particles, typically a positron and a neutral pion. with a lifetime that depends on the specific grand unified model. Current experimental bounds from the Super Kamio Kondi detector in Japan place the proton lifetime at longer than approximately 10 to the 34 years for the dominant decay modes. Next generation experiments, including the Hyperkamio Kondi detector currently under construction in Japan and the Deep Underground Neutrino experiment in the United States, will push this limit higher and might detect proton decays if the lifetime is in the range predicted by certain grand unified theories. The vacuum of a grand unified theory is qualitatively different from the vacuum of the standard model. It has a richer structure, including condensates of grand unified fields and additional symmetry breaking vacuum expectation values. The properties of the grand unification vacuum determine which particles get which masses, why the coupling constants have the values they do at low energies, and what the proton lifetime is. Understanding the vacuum at this scale would explain many features of the particle physics we observe that the standard model takes as given. The even more fundamental vacuum structure of a theory of quantum gravity remains unknown. In string theory, the vacuum is a 10-dimensional or 11-dimensional spacetime compactified to 4 observable dimensions, with the 6 or 7 extra dimensions curled up into a compact space at the Planck scale. The specific geometry of the compact space determines the effective 4-dimensional physics, the number of particle families, the values of the coupling constants, and the nature of symmetry breaking. There are an estimated 10 to the 500 possible distinct string vacua, each corresponding to a different compactification and a different set of physical laws. This is called the string landscape. If the string landscape is real, then the physical constants of our universe, including the masses of particles, the coupling constants, and perhaps even the dimensionality of space, are not uniquely determined by any fundamental theory, but instead correspond to a particular vacuum among a vast ensemble of possibilities. The question of why our vacuum has the specific properties it does, why the cosmological constant is the tiny value it is, why the Higgs mass is what it is, why there are 3 families of quarks and leptons, might be answered anthropically. We observe these values because they are the values in the part of the landscape where observers like us can exist. The anthropic principle applied to the string landscape is one of the most controversial ideas in modern physics. Many physicists find it unsatisfying because it seems to remove the question of why the physical constants have their observed values from the domain of scientific explanation. Others argue that it is the correct framework for understanding the fine-tuned aspects of the vacuum, particularly the cosmological constant, which is so small that no known non-anthropic explanation exists. The most direct experimental test of the landscape idea would be the detection of another bubble universe, a region of space-time that underwent a different quantum vacuum transition and therefore has different physical laws. In eternal inflation, the cosmological scenario in which inflation continues indefinitely in most of space, while individual bubble universes nucleate and evolve separately. Bubble collisions could potentially leave imprints on the cosmic microwave background. Searches for these signatures in cosmic microwave background data have been performed and have not found definitive evidence, but the sensitivity of these searches is limited, and future observations might reveal effects currently below the detection threshold. Returning to more immediately testable physics, the experimental program for quantum vacuum effects in the next decade is rich and specific. The successor to current precision Casimir effect measurements will probe the geometry dependence and material dependence of the vacuum force with sufficient precision to test theoretical predictions about repulsive Casimir forces and Casimir torques. the tendency of anisotropic materials to rotate in response to the vacuum force. These measurements will also provide constraints on exotic physics beyond the standard model, including the existence of extra spatial dimensions at submillimeter scales, because extra dimensions would modify the gravitational and Casimir forces at distances comparable to the extra dimension size. Quantum vacuum the change in the polarization of light traveling through a strong magnetic field due to vacuum fluctuations is predicted by quantum electrodynamics. In a strong magnetic field, virtual electron-positron pairs in the vacuum interact differently with photons polarized parallel versus perpendicular to the field, causing a small rotation of the polarization of light. This effect has been measured in the PVLA's experiment in Italy, which uses a powerful magnet and a sensitive interferometer to detect the tiny polarization rotation. The measurements agree with quantum electrodynamics predictions and provide a direct probe of the virtual particle content of the vacuum in a strong magnetic field. The ATLAS and CMS detectors at the Large Hadron Collider have also measured light-by-light scattering, the process in which two photons scatter off each other through a loop of virtual particles. In classical electrodynamics, light does not interact with light. Photons pass through each other without interaction. In quantum electrodynamics, virtual electron-positron pairs allow photons to interact, with a cross-section that depends on the photon energy and the virtual particle loop structure. This scattering was first observed at the LHC in 2017 using ultra-peripheral heavy-ion collisions, which produce intense photon fields through the Lorentz-boosted electromagnetic fields of the fast-moving ions. The observed cross-section agreed with quantum electrodynamics predictions for the virtual electron-positron loop contribution. Every one of these experiments, from the precision Lamb-shift measurements in atomic physics to the light-by-light scattering at the Large Hadron Collider, is a measurement of the quantum vacuum. They span 40 orders of magnitude in energy, from the microelectron-volt scale of cold atomic systems to the teraelectron-volt scale of LHC collisions. Across all of this range, quantum field theory with its specific vacuum structure correctly predicts the observations. The quantum vacuum is the most thoroughly tested concept in the history of physics, and yet the deepest questions about it remain unanswered. Why does the vacuum have the energy it does? How does the vacuum energy relate to the cosmological constant? What is the vacuum at the Planck scale? How does the entanglement structure of the vacuum give rise to space-time? These questions are not merely technical refinements. They are the frontier of fundamental physics. The answers will come from the convergence of multiple experimental and theoretical developments. They will come from measurements precise enough to see quantum gravitational corrections to vacuum energy. They will come from cosmological observations that track the evolution of dark energy across cosmic history. They will come from quantum simulations using cold atoms and quantum computers that can model strongly coupled vacuum states, inaccessible to perturbation theory. And they will come from theoretical insights connecting entanglement, holography, and quantum gravity in ways that have not yet been found. The history of vacuum physics is a history of discoveries that seemed impossible before they were made. The Casimir effect seemed like a theoretical curiosity with no experimental relevance until it became an engineering constraint in nanotechnology. The Schwinger effect seemed beyond any foreseeable experiment until graphene made it accessible. Hawking radiation seemed unobservable until analog systems in the laboratory demonstrated the mechanism. The Higgs vacuum seemed like an abstract, theoretical construct until the Higgs boson was detected. At the Large Hadron Collider in 2012, each of these discoveries was a window into the same underlying reality. The quantum vacuum is not nothing. It is the most fundamental thing there is. It is the state from which everything else arises, the ground of all physical existence, the field that permeates all of space and that, under the right conditions, produces matter, mediates forces, shapes the geometry of space-time, and drives the expansion of the universe, something from nothing. Not as a philosophical puzzle or a religious mystery, as a precise, quantitative, experimentally verified feature of the quantum world we inhabit. The vacuum creates, sustains, and in the long run of cosmic time will transform everything. That is not a small thing to understand, and we are still learning how to understand it fully. One final thread worth tracing is how the quantum vacuum connects to the everyday world in ways that go beyond laboratory curiosities. Every chemical bond, every biological process, every material property depends ultimately on the quantum mechanical behavior of electrons. And electrons exist and behave as they do because of their continuous interaction with the electromagnetic vacuum. The van der Waals force that holds molecules together across distances too large for direct chemical bonding is a manifestation of vacuum fluctuations. The same quantum fluctuations that produce the Casimir force between macroscopic plates also produce the attractive force between molecules, governing the cohesion of liquids, the folding of proteins, and the adhesion of biological cells to surfaces. The van der Waals force was understood classically as an interaction between fluctuating electric dipoles on adjacent molecules. The quantum mechanical explanation connects it directly to the electromagnetic vacuum, even in the ground state. Each molecule has a fluctuating electric dipole moment due to vacuum fluctuations of the electron positions. Two nearby molecules experience correlated fluctuations because the vacuum fluctuation field is shared between them, producing a net attractive interaction. At short distances, this interaction follows an inverse sixth power law. At longer distances, where the finite speed of light introduces a retardation effect, it becomes an inverse seventh power law. This long-range form, called the Casimir-Polder force, is a direct analog of the Casimir effect and was predicted by Hendrik Casimir and Dirk Polder in the same year Casimir predicted the plate force. The Casimir-Polder force has been measured in experiments, where atoms are brought close to surfaces and the force is detected through its effect on atomic energy levels. These measurements confirmed the retardation effect and the transition from the inverse sixth to inverse seventh power law, providing another precision test of the vacuum structure of quantum electrodynamics. At the biological scale, the van der Waals force underpins the remarkable adhesive ability of gecko feet. The gecko can walk upside down on smooth surfaces because the millions of tiny hair-like structures on its footpads, called seta, each ending in even tinier flat tips, called spatulae, make such close contact with the surface that the van der Waals force, summed over the enormous number of spatula contacts, produces enough adhesive force to support the gecko's weight. The gecko's adhesion is non-sticky in the chemical sense, leaves no residue, and can be engaged and disengaged rapidly by changing the angle of the seta. It is a biological exploitation of the quantum vacuum. Force engineers have attempted to create synthetic gecko adhesives using carbon nanotube arrays and polymer microstructures that mimic the geometry of gecko set. Some prototype gecko-inspired adhesives have been demonstrated that can support significant weights on smooth surfaces using only van der Waals forces. The design requirements come directly from the physics of vacuum fluctuations, translated through molecular forces into macroscopic adhesion. The quantum vacuum shapes the engineering of adhesive materials. The London dispersion force, one component of the van der Waals interaction, is particularly important in biology because it is the dominant attractive interaction between nonpolar molecules. including the hydrocarbon chains of lipids and the aromatic rings of DNA base pairs. The stacking interactions between adjacent base pairs in the DNA double helix are primarily London dispersion forces. These vacuum-mediated interactions contribute to the stability of the helix and influence the mechanical properties of DNA, including how easily it can be bent, stretched, and unzipped by molecular machines, like polymerases and helicases, during replication and transcription. The immune system relies on highly specific molecular recognition. Antibodies bind antigens with exquisite specificity because the shapes and chemical properties of the binding surfaces are complementary. The binding affinity depends on a combination of electrostatic interactions, hydrogen bonds, and van der Waals forces. The van der Waals component, mediated by vacuum fluctuations, is often significant for tightly binding antibodies where the molecular surfaces are in very close apposition. Designing antibodies with high binding affinity for therapeutic applications requires correctly accounting for van der Waals interactions, which ultimately means correctly modeling the quantum vacuum between the molecular surfaces. This connection between the quantum vacuum and life is not trivial. The specific properties of the vacuum, the strength of quantum electrodynamic fluctuations, the mass of the electron and its coupling to the electromagnetic field, determine the magnitude of van der Waals forces. Different values of these constants would produce different van der Waals forces, different molecular binding affinities, different material cohesion, different biological structures. The vacuum as it exists is a specific configuration with specific properties, and life as it exists depends on those specific properties. This is one face of the fine-tuning problem that the anthropic principle and the string landscape attempt to address. The constants of the Standard Model, which are determined by the vacuum structure of the Higgs field and the quantum fields of the strong and electroweak interactions, must fall within a narrow range for chemistry and biology to be possible. The electron mass, the fine structure constant, the strong coupling constant, the Higgs vacuum expectation value, all of these must be close to their observed values for atoms to be stable, molecules to form, and life to exist. Understanding why the vacuum has the specific structure it does is therefore not separable from understanding why the universe contains complexity, chemistry, and life. Physicists who find the anthropic explanation unsatisfying are motivated to find a dynamical explanation, a theory in which the observed vacuum structure is uniquely or nearly uniquely determined by deeper principles, rather than being one of a vast landscape of possibilities. This would be the analog of a Newtonian explanation for planetary orbits before Newton. One might have invoked a selection argument for why the planets are at particular distances from the Sun, but Newton showed that the orbits follow dynamically from the law of gravitation. Perhaps a deeper theory of the vacuum will similarly provide a dynamical explanation for why the vacuum has the structure it does. This is one of the primary motivations for developing a theory of quantum gravity. Quantum gravity is expected to become relevant at the Planck scale, where quantum mechanical and gravitational effects are both large. A consistent theory at the Planck scale might uniquely determine or strongly constrain the vacuum structure of the lower energy effective theories. The string landscape view suggests that quantum gravity does not uniquely determine the vacuum but instead allows a vast space of possibilities. The dynamical determination view suggests that deeper principles will single out our vacuum or a small class of vacua as physically preferred. This question requires a level of theoretical and development beyond what currently exists, but the direction is clear. Every precision measurement, every new quantum material, every cosmological observation, every advance in quantum information and quantum computing brings us closer to a complete understanding of what the vacuum is and why it is the way it is. The universe is not a collection of things floating in an empty container. It is a collection of fields, each in their quantum ground state, fluctuating, interacting, condensing, and occasionally producing the particles and forces we observe. The vacuum is not the absence of the universe. The vacuum is the universe in its most fundamental form. Everything else, every particle, every atom, every star, every galaxy, every thought, is an excitation of that ground state. That is what physicists mean when they say that something comes from nothing. Not nothing as emptiness, but nothing as the quantum vacuum, which turns out to contain everything needed to give rise to the physical world. Julian Schwinger calculated how to extract matter from it. Hendrik Casimir predicted how to feel its pressure. 70 years later, the predictions held. The vacuum yielded, and the universe revealed one more layer of what it is.